We've been working on solving differential equations, and we've also been looking at slope fields. We saw that one of the primary applications of differential equations involves exponential growth and decay. And so what I'd like to do in this video is take the ideas of growth and decay and sort of merge them together with the graphical connections of slope fields. And so to begin, let's take a look at 4 different slope fields. And can we look at them and figure out which ones represent growth, which ones represent decay? And then think about how you can tell. So in the letter A, I don't really see any kind of sign of an exponential growth or decay pattern. It looks almost like an upside down quadratic or maybe a part of an ellipse. So for A, I'm going to label that as neither growth nor decay. But take a look at letter B. There seems to be a horizontal asymptote at y equals 0, and the slopes seem to be decreasing and kind of flattening out there. I can almost picture that decay curve. So I'm going to label B as a decay graph. And what about slope field C? Growth or decay? Again, there's an asymptote there, horizontal asymptote, and it appears that I have an increase in slopes as I rise above the asymptote, so that would be a growth slope field. And then finally, letter D, there is a horizontal asymptote just bumped off of the x-axis right there, and it looks like I have, again, exponential decay as I fall down to the asymptote. So I'll label that 4th slope field as exponential decay. So kind of look within the pattern of all of the slopes and see if you can match one of the functions to them. What about this? Let's take away the pictures for a moment and just look at the differential equations. Here are 5 differential equations, and the question just says, are they exponential growth? Are they decay? Maybe neither, and then how can we tell? Well, with no picture, remember that we know that the rate of change, as far as with respect to time, when it comes to exponential growth or decay, is going to be directly proportional to the population itself. And so what that means is I'm going to look for some kind of differential equation in terms of y, the dependent variable. And it looks like that would be choice A. Choice B is in terms of y. I have a constant of proportionality out there of 2. Choice C would not be growth or decay. That is in terms of x. D would be a growth versus decay. And not E as well, because it's actually y squared, but I want it just to be directly proportional to that population. So A, B, and D would be my choices here. The k value would be 1 in choice A. The k value is a 2 in choice B. In choice D, the k value actually is negative 0.5, so that would be an illustration of a decay example. So let's kind of take these ideas and put them together in a couple more concrete examples moving forward. So here's what we should know. The rate of change with respect to time of the population is directly proportional to the value of that population. And if I write a differential equation to kind of describe that, we saw that just a moment ago, I'll use capital P for population. So dp dt, the population with respect to time, that rate of change is equal to k times p, where k is the constant of proportionality, and capital P is the value of the population. Now, let's solve this differential equation. So if I separate the variables, and we'll integrate both sides, left and right, so natural log equals kt plus c, solving for p will give me this expression of c e to the k times t, and I can basically write that as population equals c e to the kt. We would check the plus or minus on that as well and figure out what the constant of integration would be. But there it is. There's the solution. So dp dt, if it's directly proportional to the value of the population, we can just jump right to that expression of y equals c e to the k times t. Now, some parameters to just note here. Don't confuse the c and the k in these exponential growth applications. So c is that constant that comes from integrating, but lowercase k is the constant that comes from the definition of the rate of change. In this case, it's the constant of proportionality. And again, if in growth versus decay parameters, when k is positive, we have exponential growth. When k is negative, we have exponential decay. So here's a challenging example, number 5 on this document. it says we have this experimental population of fruit flies, and it increases according to the law of exponential growth. Well, what that means is I can actually apply the P equals C e to the k times t formula to this situation. I can just jump right there without having to go through the process of solving a differential equation. We can make that claim. And it says here, so I basically have two conditions here. At time 2 days, we had 100 fruit flies, and then at time 4 days later, we had 300 fruit flies. And so what I want to actually do here is set up a system of equations, and I can solve that system to solve both of the constants. So here's what I might do first. We'll plug in the 100 for the population parameter. I don't know what C is yet, e to the power of k times 2, because that took place on day number 2. Let's solve that for C, actually, and we can write that as 100 times e to the negative 2k. I'll leave that in the parking lot for right now. What about the next parameter here? So we had 4, 300. When the population of fruit flies was 300, then C e to the k times t, that was on day 4. So I can, again, just jump right to the exponential growth equation. Now, let's substitute this expression for C into my equation over here. So 300 equals 100 e to the negative 2k times e to the 4k, which will essentially be 300 equals 100 e to the positive 2k, divide by 100, and now I'm ready to use my calculator to solve for k. Take the natural log of both sides and then divide by 2 to isolate your variable of k. You can check that math on your own, but the k value here ends up being 0.5493, and then I can plug that number k in. Let's plug that back in here to my equation for C. What do we say? C is equal to 100 times e to the negative 2 times k. So plug your k value in. The question here says how many fruit flies were there in the original population, and that would be basically your capital C value. So compute this on the calculator. With your k value plugged in, we should get around 33. If I round to the nearest whole number, we should get around 33 fruit flies for that starting amount. So kind of a challenging problem. We have two ordered pairs. They did not give us the initial value when time is 0. That would have been a little bit more straightforward because we would have known the C value right away. In this case, we had to use the two ordered pairs to solve for that missing C value. Now, what's a question that you might see on a multiple choice test or maybe on an FRQ? Well, here's one, not related to any kind of word problem, very straightforward. 7 says the rate of change of y is proportional to y. So that means that dy dx is equal to k times y. It says here that when x is 0, I have an output of 4. And that's nice because if I have the 0, that would be the y-intercept essentially. That means my C value here is going to be 4. I also know that when x is 3, y is equal to 10. So let's use those two data points and write an exponential. In this case, it looks like a growth equation. We're going from 0, 4 to 3, 10. So I have a positive k value. And I can write this expression, y equals 4 times e to the k times x. I know that the C value of integrating is going to be 4 from the ordered pair 0, 4. I don't know what k is. Let's plug in 3 and 10. So 10 equals 4 e to the power of 3 times k. I can solve for k, and I'll just let you maybe check that out on your calculator. When I solved this, I got a value of 0.0911629 and some other numbers after that. We don't want to round too soon. Don't forget that it's not really appropriate to round prematurely. Otherwise, you're going to be carrying that round off error with you in future calculations. Maintain 3 decimal place accuracy throughout and try to avoid rounding until the very last step. So there's our k value. The equation then for the exponential growth is y equals 4 e to the power of 0.0911629. Plug in that 6 right there, and then we'll solve for y to get our solution. Y is approximately equal to 6.931. So there we go, taking just a sort of a generic example of exponential growth and applying it to a problem like that. Now, one last question to close with, and that looks like this. One more, again, I like this idea of kind of marrying the slope field to the actual differential equation, being able to see both and interpret the patterns in both. So number 9 says, what does this slope field suggest about the exponential situation? Well, I see that there's clearly an exponential decay curve. So I'm going to label this graph as a decay situation. But then number 10 is the follow-up question. It says, which of the following differential equations would represent the slope field? And so right away, I'm going to eliminate A and C. They're in terms of x. But if I'm dealing with exponential growth or decay, well, then that means I need to have some kind of direct variation with that population or with that dependent variable of y. And now the issue is it choice B or choice D? Well, remember, it's a decay graph, so that means my k value has to be negative. And don't get tricked here. Both of these numbers out in front are negative. However, if you distribute, we see in choice D, negative 0.7 times y plus that 3.5. There's the negative value. But if I do a negative 0.7 times a negative 1y, this is going to become a positive 0.7 y up in choice B. Oops. Pardon my stylus there. So what that means is I have, which of those two is a negative k value? Well, that would be choice D right here, that negative 0.7 multiplier on that y value. So choice D is my solution. That's going to be the match of the slope field that's given. So those are some connections between the slope fields and the algebraic approach to solving differential equations and how they all relate to exponential growth and decay. I hope that was helpful to you. Good luck with solving the rest of your problems.